Hello, everyone. Thanks for joining us for another webinar on Progenesis Academy. We are thrilled to have you here with us today for a truly out of this world topic. Progenesis Academy is an education initiative by Progenesis dedicated to sharing cutting edge knowledge in reproductive medicine and genetics with professionals around the world. Through webinars like this one, we bring together scientists, clinicians, embryologists, and innovators to explore the future of reproductive medicine. Our webinars happen lively every second Wednesday of each month, and on the following day, we post on our channel on YouTube, Progenesis Academy. Please, I invite you to subscribe, like, and watch more than 200 videos with very insightful knowledge. This is also very interesting because with these live webinars, you can get ABB credits after watching it live. Today's session, IVF in Space, Are We Ready?, explores the frontier of assisted reproduction in space environments. We'll dive into the technological and biological challenges of enabling human reproduction in orbit. We are honored to be joined by leaders from SpaceBorn United, who are actively designing the tools and protocols to make IVF possible in space. I will first introduce our first speaker, Dr. Egbert Edelbroek, founder and CEO of SpaceBorn United. Dr. Edelbroek leads a pioneering space biotech company focused on improving IVF on Earth while enabling human reproduction in space. Motivated by his personal connection to assisted reproduction, he now spearheads the development of automated IVF systems for space missions. He holds a PhD in organization development, integrating biology, neurology, and psychology. Dr. Egbert will introduce SpaceBorn, discuss their mission, and provide an update on current developments. Our second speaker is Dr. Sheela Ali, who is a board-certified high-complexity lab director with over 17 years of experience in human IVF. She currently leads multiple IVF programs and is a recognized leader in embryo biopsy, AI in IVF, and lab quality systems. She is the Chief Medical Officer at SpaceBorn United. Dr. Ali will discuss the benefits of IVF in space science that can be applied to IVF on the ground. Third, Dr. David Cullen, who is professor of astrobiology and space biotechnology at Cranfield University. Dr. Cullen earned his PhD in biotechnology from the University of Cambridge. After a pivotal role in the ExoMars Life Marker chip instrument, he shifted his focus to the integration of biology in space systems. He has collaborated with SpaceBorn United since 2017. Dr. David Cullen will review the logistics and engineering of their mission and discuss challenges and limitations. After presentations, we are going to play a very interesting video about the device for IVF in orbit by SpaceBorn United. And last but not least, we are going to open this session for discussion. So we are going to respond to your questions that you can start sharing on our chat. Please welcome our speakers. Dr. Egbert Edelbroek, you can start.
Thank you so much, Fernanda, for the introduction and the kind words. It's a pleasure to join this group and tell the audience about our goals and work. I'm going to share my screen. I have some slides. So, are we ready for IVF in space? That's the topic for today. And let me start with explaining what the key goals are for SpaceBorn United. We're focusing on two strategic goals. The more short-term goal is to enhance IVF treatment on Earth, by doing research in space, by performing IVF in space. The more long-term strategic goal is to enable stages of human reproduction in space environments. For the last couple of years and the next couple of years, this is focusing on the very first stages, so conception and early embryo development. We are trying to achieve these goals by developing technology. We are re-engineering existing assisted reproductive technologies to make them work in space. And this results in a small shoebox size automated mini lab, an IVF mini lab that can operate in space. And we also develop specific space missions architecture in order to make this device, this mini lab work in space. So we call this mini lab the ARTIS mini lab. That stands for Assisted Reproductive Technology in Space. And why would we do this? Because it creates benefits for enhancing IVF in space. Applying the technology and doing the IVF in different gravity environments is expected to result in some improvements that lead to better success rates of IVF treatment, shorter treatments, reduced medication costs, also improved embryo selection, improved culture medium, and also reduced patient burden. The scientific background of this will be, Sheela will be elaborating on this a little bit more in her presentation. So I will be focusing on how we are achieving this. The question, are we ready for IVF in space, has different perspectives. Of course, there's the biomedical and the space technological perspective. The SpaceBorn is preparing to do this. So we have our roadmaps in place, our research roadmap, our hardware development roadmap. We are re-engineering these subsystems, these existing IVF platforms, and we're testing the subsystems. That's all in progress. Similar for the space technology perspective. We are validating and optimizing the space mission architecture and the space missions roadmap. So that's all in progress. But of course, this question is not about, is SpaceBorn ready for IVF in space? The key question is, are societies, is humanity ready for IVF in space? So that includes the more ethical perspective and some legal elements. I also included the agency's perspective because this is a very big topic. It's a huge topic, huge challenge, and one would expect space agencies to address this. But because this is ethically quite delicate to expose gametes and embryos to the hazards of space, it is ethically too delicate for space agencies to spend taxpayer dollars on this challenge. They're open about it, and that gives SpaceBorn a reason to exist. They're supporting biotech research companies like us to address this crucial challenge for humanity. But there's a lot of ethical debate about this, and we were trying to support it. We're taking part in webinars like this. We're initiating related discussions. We're making papers about it, and we are very blessed with the support we get in navigating and identifying ethical considerations related to our space missions and our IVF in space. We're supported by NASA-funded teams that combine experts from Baylor College of Medicine and the Translational Research Institute for Space Health and more. So we're blessed with this support because this is a very important element for SpaceBorn. So What have we been doing and what will we be doing? What is our roadmap and what is the progress? So for the first couple of years, we've been focusing on studying the conditions so that was 2020 and onwards, studying the conditions for reproduction in space, for different stages of reproduction in space, including the space technological conditions. That translated into research and hardware development roadmaps and ethical approval steps. And onwards, we've been validating our space mission architecture, and with our extending space missions roadmap, we continue to optimize these. Last year, we've also started testing different subsystems from our ARTIS mini lab with the help of various universities, including especially Ghent University in Belgium. This year, we want to have a first test in space, actually. We're going to have a very early prototype of the ARTIS mini lab to test in space. Also this year, we continue the testing on the ground, testing on Earth, and we will have the support of ESA with their random positioning machine. That's a multi-axis rotating device that is basically creating artificial lower gravity levels. So it simulates part of the space environment. The next step next year will be a space mission where we will have mammalian embryos inside our mini lab to develop in space. 2027, we plan to actually do the first IVF procedure. So we will do conception in space. Animal models, so we will be conceiving mouse embryos and early embryo development in space. Eventually, we will also pause the embryo development by cryogenically preserving the embryos to protect them for the rather violent re-entry maneuver from space back to Earth. There's a lot of vibration, there's a lot of G-forces, so we want to protect the vulnerable embryos for that journey back to Earth. And we hope and we think we will be allowed to do human IVF in space by the end of this decade, perhaps already in 2029. And yeah, that's going to be a huge milestone, of course. So that's the roadmap for the next couple of years. So the technology, what is that about? A very important part is the microfluidic disk that is basically using lab on a disk technology, miniaturized lab in a rotating disk, and the disk is rotating in order to provide artificial gravity levels that we want to study. We can create Earth-like gravity, but we can also study, for example, the lower gravity on Mars, the Martian gravity environment, or other lower gravity levels in between. We want to measure the health of the embryo development with different sensors, visual sensors, micro cameras, but we also want to measure a lot of other biological variables that Sheela will elaborate on a little bit. Also because what we expect is if the embryos develop in a different gravity environment, then the biology will change, and we expect some of those changes to be beneficial. That doesn't mean that we want to send many gametes for fertilization in space because there could be benefits. No, we're going to do a few missions in space, which will result in improvements that will be applied on Earth for the thousands of patients that use normal Earth-based IVF. Our mini lab also captures the data from the experiments both inside the mini lab, and it will be transmitted back to ground stations. It's a pressurized casing. It's like a small shoebox size device. There's some embryo incubator-like life support systems inside. It's going to be remotely controlled. It's going to be operating in an unmanned satellite. There's not going to be people around to control the device. It's remotely controlled, automated. And as I mentioned later on, we will also include cryogenic or pharmaceutical fixation application. So that's in a nutshell some of the key elements of the mini lab. We could only do this with a great team. You will be listening to Sheela in a moment and to Dave Cullen, but we have many more experts who are making this possible. And this is actually only a sample. There's more team members, but these are the most important ones. I know there's quite a few people from Brazil listening and watching today. We also have Dr. Rafael Elias Marques from Brazil in our team. We're very proud that he's helping with the bioethics part of the work. But I'm looking at the time. I'm going to wrap up. We cannot do this without the valuable help of research and industry partners. Several universities. Cranfield University has been supporting from the start. Lately, Ghent University is joining. In the Netherlands, we have the Eindhoven University of Technology. Many other technical partners, research partners, space technology and launch partners. And obviously, last but not least, the partners in the fertility sector, like Progenesis and Vitrolife. One thing that I did not reveal yet in our progress is that we already did the first space mission. It's no longer a plan. Last April, I was blessed to be witnessing this launch from Cape Canaveral in Florida, April the 22nd. We had a successful first validation mission where the first prototype of the ARTIS Mini Lab was tested in real flight conditions with pretty good results. Fueling us for our next mission, where we'll test a more mature version of our mini lab for more progress towards actual IVF in space. I look forward to your questions, and we're going to move over to Sheela.
Thank you, Doctor. Thank you very
My
much.
pleasure.
Yeah.
Perfect. Thank you so much for having me here. And I really feel that I have very exciting information to share because IVF in space is just a new concept. However, we don't realize that, we have been, as humans, been in space for a significant time now. So it's great that we're able to engage and raise awareness about the programs that we are working on, our science and our background through group meetings such as this one. And I'm further excited that now with, a majority of the attendees which have background knowledge in IVF can really relate to this and become more excited in terms of what other opportunities there are as we look into the future, as we are experiencing, this translation phase in our work where we're moving towards automation and AI has become more of an integrated part of our world. May I continue, or did Dr. Fernanda, did you want to add?
Please, you can.
Okay, excellent. Excellent. So I'm going to start off with some background. Many of you may or may not have known that the space environment, namely, the International Space Station, has been continuously occupied since November of 2000, which now marks 25 years of humanity in space. This is a significant time. And if we think about the researchers and the astronauts that are up in the space environment, these are usually astronauts that have to meet a certain level of criteria, which means that they are likely in their reproductive years and are waiting and delaying their family planning until further down in their career. So these are individuals that will likely become impacted by the hazards of space, as Dr. Egbert just mentioned. So we're talking about microgravity conditions for extended periods of time, space radiation, to name a couple. And then, of course, the circadian rhythms changes. So at any time, a crew of 6 people that are that are in the space environment travel at 5 meters per hour, and they orbit every 90 minutes, which results in 16 sunrises and 16 sunsets per day, which is incredible if you think about, how our circadian rhythm helps with our metabolism and our overall health and body environments. So as these individuals are in space, and we're concentrating in this particular webinar on their reproductive function, how does sleep deprivation or changes in their body chemistry or their environment, and namely microgravities, which creates, this sensation of the absence of gravity, which results in the floating feeling, is going to impact their overall cellular function and reproductive development. So to date, a microgravity lab in the space environment has now hosted more than 3,000 research investigations, which tells you that constant funding into the space research projects allow us a very unique environment to test various subsets of benefits that we can bring on the ground. So the space environment is not only just for space exploration, but it's actually benefiting, helping us understand how the biology that we can then bring that science and that insight onto the ground and help with our overall healthcare. And I'll go over some of those momentarily. Some of the findings from these research projects include that the gravity itself induces biological responses, particularly with gene expression, cellular functions, overall systems at a whole organism level. Also, the analysis of positive and negative early development outcomes, such as embryogenesis and cross-generational effects of cosmic radiation and microgravity, have been known to identify certain areas of embryonic development which are impacted. Now that we know what those areas are, we can focus on them to help us understand what we can adjust to then help bring that science onto the ground to improve our overall outcomes. There have been reviews of mechanisms that are known to mediate developmental responses rather, to stimulate microgravity on Earth and spaceflight experiments. There have been gender-specific differences that were discovered and developmental responses, which we at SpaceBorn United plan to incorporate into our research experiments. Over 2,000 space research experiments in the fertility sector have been proven to be beneficial in terms of either in partial gravity or in microgravity conditions, which help the overall biological systems. Next slide, please. So as we mentioned earlier, there are two focus areas of SpaceBorn United. We're focusing on the sector that is focused on space exploration and investigating habitats in the future in space as humanity expands. But we're also focused on a more immediate benefit, which is how can we learn from these insights and then bring them down to Earth for a more real-time benefit. Next slide. And that's the section that I'll be focusing on. So in terms of looking at all of the challenges that we're facing in IVF today, it turns out that these challenges are actually serving as a catalyst for tech innovation. And this is true not only for us with SpaceBorn United, but we see that in all of our meetings that we attend, our webinars. We're focusing on AI and how we can incorporate automation into our laboratories. So these challenges are fuel to quickly advance to the next stage and show improvements in our science. So our space-focused vision as SpaceBorn United is a resultant of some unique space context challenges. And the subsequent IVF hardware and IVF operations development have the potential to push the IVF innovation for the benefits on the ground in our lifetimes. Without the space challenge concept, this continuous space Earth-based IVF development may just simply occur over a longer period of time, and it would just be a slower progress. Specific benefits from biological research and biotech in space have resulted in a benefit in various components of healthcare. So namely drug development, tissue engineering, gene therapies, tissue regeneration, novel immunotherapy, which we know that immune cells behave very differently under microgravitational conditions than they do under the stressors of gravity on Earth. Cancer treatment options in these environments are more promising, namely gene regulation under microgravity is different and it's giving us insights. Embryology in particular, which what we're interested in here, we're looking into optimization of embryonic cell differentiation and then understanding the developmental stages and what hinders certain stages so we can overcome those challenges. And many of the focus areas that we're particularly interested in, and I know the rest of the audiences also is, of course, environmental challenges and stresses that are induced by the environment. Having embryos develop outside of, the body and into a stationary culture dish, and then how that impacts their overall blastocyst conversion rate, and then obviously down the line, pregnancy outcome. Next slide. So when we're looking at the different benefits, the goal is to identify these adoptions and then quickly replicate those conditions on Earth through research and science. And then this way it'll benefit all of, IVF in many ways. So some of the applications include, and the benefits include, shorter IVF treatment and medication costs, namely through drug development. So the expectation is, as we continue our research, that we are going to be able to target specific molecules that will result in an improved medication for ovarian hyperstimulation. Currently, our challenge is that there are some medications that are applied in significantly high doses, which not only add to the overall cost of IVF, but also induce challenges or subject, women to unnecessarily high hormonal states. And then at the end of it, we're still seeing, despite the high use of gonadotropins, a low blastocyst conversion rate. So how do we combat these challenges to introduce a drug that is more targeted, that is more effective, and also more economical? Next is improved embryo selection. This is definitely something that AI is looking into, but we're looking at a more scientific approach. So identifying biomarkers for embryo competence that can be included in a more comprehensive genetic panel. And that will hopefully optimize the conditions and help us understand how microgravity modulates development of an embryo. And currently, what we're using is, of course, PGTA technology, which has significantly improved our outcomes by helping us identify the chromosomally normal embryos in terms of whole chromosomes or segmental chromosomes, loss or gains. But we still face challenges even if we're transferring euploid embryos. We're noticing that not all euploid embryos implant. There are some that are, unexplained implantation failures, or they'll implant and then we face a pregnancy loss despite, the most up-to-date technology that we're using in PGT, which means that we can possibly incorporate advanced technology to enhance the current PGT state. Next, we're looking at, and this is probably my favorite here, is improved culture media. So a novel culture formulation, which will include, we'll learn from metabolomic profiling, which can help us inform us of energy requirements of the developing embryo. And we can understand where the resource allocations are to identify specific supplements or additives, such as survival proteins. So these are stress proteins, for example, heat shock proteins, which play a very important role in protein folding, intracellular transport, and repair or degradation of proteins. If we can identify these additives and include them in our culture media, what we hope to see is that these additives will then help aid to offer resilience to environmental stressors as the embryos are developing, and reducing the impact, negative impacts anyways, on embryo development during the time that they're in culture. Next slide. Automation. There are several companies that are working on IVF automation, but we just saw a close-up version of the SpaceBorn United lab on a chip earlier today. So the image on the top left-hand side of the screen that you're seeing is basically a representation of what the rotating disc looks like in the IVF chamber of the SpaceBorn mini lab. So if you can imagine, the disc is rotating due to centrifugal force, and that force is allowing for the channels within the disc to have media flow through the chambers. And this continuous flow of media will help replenish the media, but not only that, it will allow the gametes to mix, which is amazing, because then it automates several key steps of the IVF process, which currently are highly dependent on technicians or embryologists. I am also an embryologist, and we work very hard to make sure that our skills are not only the best that we can get them, but also have little to no variability within, at least within a certain lab intratech. But variabilities do exist because, you know, there are certain differences that unfortunately we can't avoid. And what in science, what's important is to ensure that the variability is minimal for reproducibility, but also to ensure that there is, you know, there's a flow in terms of your effectiveness of handling cycles, repeated work to make sure that those steps, you know, the repetition doesn't cause highs and lows. And then all of the manual steps that bring that variability are reduced with automation to provide a more updated outcome. So the biologists, the embryologists that are in the laboratory are then focusing their workload on QI, or quality improvement, rather than, you know, combating the challenges of intratech variability. Next, we have on the bottom left-hand side of the screen, the culture plate, which, you know, shows you the design. And I believe we have a more updated design now that Dr. Edelbroek showed. And so what we're doing is we're having the culture ova and the embryos that are held in place. And then the media is, of course, flowing. So it allows us to have individual chambers for these ova, and then, of course, zygotes and embryos downstream. Cryopreservation occurs in place. So the embryo is not moving during the cryopreservation. And what that allows us to do is also to have the final chambers that the embryos are cryopreserved in, single embryo per chamber, are then, in terms of logistics, having robotics so these final vitrified embryos can then be removed by these just as these individual chambers. The robotics will load the gametes. The rotating disc, of course, through gravitational forces, will allow for the mixing of the gametes. And then the robotics will then take these individual chambers once the embryos are frozen and move them to a liquid nitrogen base. The AI and automation will allow us to automatically grade, generate reports for patients and providers alike, and then hopefully use integration to then remove the manual administrative steps. Embryo selection is a big one, and it's definitely something we're looking into for AI. And as we have these live cameras, micro cameras on the development of the embryos. So morphokinetic use as part of the final selection tool is definitely part of the plan. There are other benefits also, such as spent media and sampling, which can be done. And we're hoping that, you know, as you've heard, Progenesis is a partner, and Progenesis, some of their research focuses on spent media analysis and metabolomics. And we're hoping to understand how we can gain information and insights with spent media analysis to identify biomarkers for competence, and combine that with cell-free PGT in hopes that one day the invasive practice of trophectoderm biopsy will then be a thing of the past, and we can use this enhanced genetic testing to then offer a better embryo selection and hopefully increase outcomes. Next slide. There are other benefits that we're focusing on that are non-fertility, and some of those include aging and longevity insights. So our focus area is beyond fertility. However, fertility is our main area of focus. So cellular aging and rejuvenation via looking into epigenetic research and under various gravitational conditions will help us provide insights that we hopefully can apply to IVF and understanding how we can better develop the trifectoderm, how we can better develop the ICM and give them both the most optimal conditions to hopefully improve not only their overall quality and health, but also blastocyst conversion rates to help with, again, those costs. Drug testing is another one. You know, the SBU lab offers a mini environment, and we know that in the space environment, generally, those stressors help speed up the aging process in tissues. And these, you know, these medications that are being tested or drugs that are being tested could yield faster results in that space environment using the SBU mini lab compared to terrestrial drug testing. Also investigating reproduction in space. So as humanity is discussing, exploring, you know, expanding its presence beyond the Earth environment, the prospect of human exploration and settlement in the past was a tangible event, and now it's becoming more and more objective. As we are noticing that the space, the space environment is opening up to more leisure space flights through some of the more recent programs, we are exposing individuals with very many different health conditions into the space environment, you know, and we are making humanity in general having them become, you know, more comfortable and accept the space environment as an exploratory measure. And as we're doing that, it's not such a big leap that we might one day, you know, offer flights to other planets like Mars or the moon. And with that, you know, we want to pave a way where we can prove or demonstrate that at the very least, embryonic development and viability is, we're able to achieve that. So in terms of being able to continue our research and being able to raise the funding to do so, it's important to demonstrate that to stakeholders. So that way we can justify the continued research into space. Also, partial gravity and independent settlements into these other planets will one day become a more realistic approach. And it's, of course, the bigger goal. We may not get to see that in our lifetimes, but of course, through our research experiments, we're hoping to understand what the engineering requirements are for these habitats so they are cost effective. They're not large or grand scale, and that'll allow us to have a more comfortable environment in these space conditions. So that way we can continue to thrive instead of just hoping to survive in these new environments. Next slide. And those are my references. And I'll give that back to Fernanda to introduce our next speaker. Thank you.
Thank you, Dr. Sheela, for your excellent presentation. Very interesting. So now I invite Dr. David Cullen.
Okay, let me just share my screen. Hopefully you can see that.
Yes, yes,
Just
perfect.
move a few things out of the way so that I can. Okay, so I'm going to now take a slightly different viewpoint. So as you can see there, my background is really a foot in both camps. So I originally trained as a biochemist, biotechnologist, and then somehow accidentally mid-career stumbled into the space sector, and now been in the space sector doing biology and biological relevant instrumentation now for about 20 years. So I can see this from both perspectives, from the perspective of a bioscientist, but also as a space systems engineer. And so the idea today is to really kind of look at what we're planning to do in terms of kind of IVF in space, the artist concept, mission concept, but from a space systems perspective rather than from a kind of bioscience perspective. And I'm assuming the audience today is primarily from the bioscience, IVF kind of domain, and therefore not particularly familiar with some of the concepts I'm going to be talking about. They're all going to be very top level. There's an opportunity for you to get to see some of the top level issues from a space engineering point of view of trying to do biology in space, and especially the situation with kind of IVF and what we're planning to do. So I think the next slide just gives you a quick flavour of what I'm going to do. Some of this will be repeating what you already heard, but from a different perspective, and therefore I'll step through those bits quite quickly. But there's really 7 key points, basically 7 slides. One is to have, again, a look at the space environments and the bits we're interested in. Touch upon, and again, I'll step through this quite quickly, the key bits of our IVF workflow we're trying to do in space and the bits we're not. Then starting to look at this really from a space systems point of view, look at the generic timeline and workflow of what a typical space mission involves, and where some of the challenges, the special challenges arise when trying to do or fit IVF into this. Again, looking at one specific aspect of that, something we call late access to the payload in the launch process, and I'll explain a bit more about that. Also talk about, again, the spinning disc, and again looking at that from a different perspective as to why we want that spinning disc to do the IVF in, that lab on a disc. And then lead out, again, with our the overview of what we're trying to do, again, from a space systems point of view. And of course, just give you a flavour of what some of that means in a bit more detail. And of course, again, a bit like Egbert mentioned earlier, what you see there is actually our first flight of hardware in space. And a key thing which to look for there as I go through the rest of this is it was hardware in space. That in this first implementation in April of this year, it was just hardware only. So we didn't have to worry about keeping the biology active during all the pre-flight aspects, which I'm going to focus on going forwards. So to some extent, it was relatively easy. It's going to become more challenging when we try and have biology within the payload as we integrate it in these flights. So again, busy slide, but I'll just pick out the key things. We already know that the 2 bits of space environments we're interested in is changes in gravity and changes in ionizing radiation levels. We know that Earth life, including humans, have evolved in a 1G environment. And if we go beyond the Earth, we find a whole different series of those, be it microgravity in low Earth orbit, microgravity in deep space, 1/3 Earth gravity, roughly on Mars, or 3/8, and of course on the lunar surface. And of course, we can also generate artificial gravity using centrifuges, which we'll come back to, because effectively that's what the spinning disk is. And the consequence of all this is although we've done lots of experiments on the ISS, as a data set, it's really still very poor. We still don't have a really deep understanding of how altered gravity levels really affect the kind of details of human or Earth biology. We have some understanding, but definitely not a deep understanding. And of course, ionizing radiation. When we go beyond the Earth, we see a different level of ionizing radiation to what we see here on Earth. Because remember, we live in an ionizing radiation environment, and therefore Earth biology, including humans, have evolved to deal with a certain level of exposure to Earth levels, surface levels of radiation. We go to space and we see more radiation, so we need to consider that. And just to give you a flavour here, in this line here, on the surface of the Earth, if you're familiar with radiation units, the biologically weighted radiation dose is called sieverts. So on Earth, we as humans absorb around about a few millisieverts per year. Inside the ISS, a human receives a 1 millisievert per day. And on a return trip to Mars, obviously this is over an expensive series of period of time, we can receive up to 1,000 millisieverts, 1 sievert, which is a significant amount. So we need to think about that. But in contrast, the actual effect on Earth biology is much more well understood because we can replicate those situations on Earth. There are some other things which we think about when we're designing space systems, but I think not relevant for today. Today, that's things like providing atmosphere contribution, composition and such. But to move on, again, this is something you should be familiar with. What are we trying to do within the IVF workflow? So again, really simplified. So on Earth, we're doing pre-flight, a whole series of things. We're acquiring gametes, we're processing those, we're characterizing them. And the thing I'm going to focus on is storage and transport, because then we need to store them, transport them to the launch site, store them at the launch site, store them in the payload, store them kind of on the launcher. We then launch, and of course in blue is the bits we're trying to do in space. So we're trying to take those kind of cells, those gametes, from whatever storage it is, and then do the fertilization and assessment in space to do, at least in the early kind of artist missions, to then do the incubation and the assessment of the early embryo development over 2 to 5 days, and then of course put back into storage and return back to Earth, and then do things post-flight after it lands back on Earth. But again, thinking about having to maintain storage conditions until we get those embryos or that material back into an institutional laboratory. And one of the key things is in this kind of box here is that on Earth, you're all familiar with using liquid nitrogen as the basis for cryogenic storage and preservation of samples. And that the logistics of that, the supply chains, is obviously well developed. You don't think about it, it's just there, you do it. In space systems, it's very, very different. We find it a great challenge to try and simply use cryogenic liquids in space systems, especially in the context of a small payload to do IVF. And so certainly for the early implementations of the ARTIST kind of payloads, we're not looking to use cryogenics in flight. Later, much further down the line, more likely, but in the early stages, we're not expecting to be able to use certainly liquid cryogens as part of the kind of early flights. So moving on. So what I've done here in blue is what we, from a space systems point of view, think about. And of course, in orange is obviously the IVF. And of course, what we need to do in almost my last slide is to really show the integration of things. What we can't do is treat them as separate things. Although at the moment, it's often the default of lots of people who are working on this is to kind of separate the two out. So what we do in terms of blue, the normal space situation, is we have a ground segment or pre-launch phase, and that can last anywhere from months to weeks to sometimes days, but mainly months and weeks. And I'll explain a bit more about that in the next slide, where we hand the payload over to the integrator, and then they check the payload integration into the launcher, into the spacecraft. They do all kinds of checks, which takes weeks or months, often under conditions where the payload is not powered and the environment is variable in terms of temperature. Historically, this was okay because most of the payloads were just physical hardware, electronics, other things, which didn't need to be powered on. They didn't need to be temperature controlled and such. There was no degradation. And so therefore the term late access has emerged for that subset of space missions where that just isn't really compatible with what you're trying to do. And you need to have late access within this ground segment to load in the time sensitive or environmental sensitive components of your payload. So that's why the term late access is something that we in SpaceBorn get really kind of involved in. So this ground segment, potentially months, hand over your payload, months disappear before you launch. Then you have the launch segment, which of course could be minutes. Literally the point where you're going to light the engines to getting into low Earth orbit is a matter of minutes. But that doesn't always happen like that. There can be launch delays, launch scrubs, weather can happen, something can come into the kind of flight safety zone of the launch site, which means the mission is scrubbed and perhaps flown the next day. And again, if you've got time sensitive, environment sensitive components of your payload and you've suddenly got to wait 24 hours for the next launch opportunity, and you don't know that's going to happen until literally the point it was originally supposed to launch, again, that's got to be catered for. Of course, you then get in space, you've got the space segment. That's where the IVF, obviously, or steps, the important steps we're focusing on will take place, the fertilization and early development. And of course, that could be minutes. The flight of in April this year, that technology demonstration, no heart, no origin, that actually was only in low Earth orbit for a matter of a few tens of minutes. The nature of the mission meant that was perfectly okay for what we were trying to achieve, but it didn't even do a full orbit of the Earth. Of course, for the IVF experiments or demonstrations, it will be orbiting Earth for a number of days. We then re-enter. Once again, the actual re-entry, once you start it, is over within minutes. But once again, there can be unexpected delays to that where it's postponed and such, and that's got to be catered for. And of course, then the ground segment is post re-entry. But again, depending on where you're landing, how quickly is that payload going to be left on the ground before some human comes up within a kind of chase vehicle, and then how long is it going to be before it gets back to some institutional facility where there is really controlled conditions. So again, from an IVF perspective or IVF viewpoint, hopefully you can start seeing some of the challenges. So the next slide, I think, is a really busy slide. I'm just going to pick out a few things. It's really going into this late access. So I think I've covered some of this already. So really what we're dealing with at the moment is a legacy of what has happened in the past in some space systems, which is basically very infrequent flights, therefore wanting to be very risk adverse because you only get one chance. So therefore you hand your payload over weeks to months in advance so that the payload integrators and the spacecraft operators can really check to make sure that there's nothing wrong in terms of the interaction with the payloads with the spacecraft system before they launch. That's the reason why there's this long typical kind of delay from handing over to flying. So there's all kinds of reasons. There have been some biological experiments which can cope with that, but they are really quite a specific subset of biological experiments where the biology is naturally in a dormant, dried down state of some kind, where it's quite happy to sit for weeks or months in untemperature controlled conditions. So we're thinking about dried microorganisms which are rehydrated in space, dormant seeds, small animals like tardigrades which can go into an anhydrous state. And I won't go through the kind of because I think it's pretty obvious to kind of most of the audience that there's the challenge for really delicate human samples such as gametes and embryos in terms of being time sensitive and being sensitive to the environment in which they're stored. Clearly there are some key exceptions. We do fly humans into space, and there's already historically the space shuttle and now the ISS, there is the ability to hand over materials a few hours before launch. But they are really only in these human kind of spaceflight systems, and those human spaceflight systems tend to be very expensive. They don't fly very often, so it's not really a long-term viable way to do biology in space. So what we need, so we're assuming that most of our flights are going to be in kind of uncrewed space systems, and therefore we are in quite a good position in that there has been a revolution in the space sector. There is now other reasons why people want to fly biology into space, almost the commercialization of space, using space or space environments to develop better pharmaceuticals, potentially even to manufacture pharmaceuticals. So because of that, there is now a whole raft of new types of spacecraft, space operators, which are trying to develop systems which do allow late access. So although it's challenging at the moment, over the next 5 years, we expect to see a number of kind of new systems where late access for biological samples becomes easier, which is an important thing to kind of plan for. And in fact, the flight we had in April of this year was with one of those new startup companies, which is developing an automated Earth return capsule, which eventually will have kind of relatively easy late access for biological experiments. So one last major kind of slide before I then start wrapping up. So this is coming back to this idea of the spinning disk. And where did that idea originally come from? So it actually developed quite early on within the kind of development of SpaceBorn. So this is the argument for that, the argument we created. So I'll step through them kind of one by one. So we assumed that the goal was eventually to have human reproduction in space. And of course, we wanted to do that, or want to do it in the future, with broad human societal approval. But we want some of those steps, which would need kind of societal approval, ethical approval, if you want, to take place in a relatively short timescale. So therefore, how do we get societal approval? Of course, we go to the existing regulatory bodies and go through their kind of processes to get approval. And of course, we assume that they will not do anything special about space. They will simply look at it from a human ethical point of view, trading off using the existing standards of risk versus reward. And therefore, the consequence of that is if we try and do any of these steps in altered gravity, be it microgravity, then we are unlikely to get any approval at the moment. Other mammalian model systems, different issue, but for human systems, obviously that's a challenge because we simply don't know what the risks are. We haven't got enough understanding of the effects of gravity on human cell physiology, let alone reproductive physiology, to be able to have the same kind of certainty or probability of low risk that we would normally expect to see kind of when arguing cases on Earth. Therefore, if we assume we need societal approval, what we need to do is to make the beyond Earth setting look to be like a normal IVF setting on Earth, where approval is already happening. Therefore, we need to have similar levels of ionizing radiation and similar levels of gravity. Radiation, I'm not going to talk about too much. It's challenging, but not so much of a challenge compared to gravity, in that choosing orbits, duration, shielding can get around that. But the gravity, how do we get rid of microgravity? Well, obviously using centrifuges. So spacecraft centrifuges to create local gravity, either kind of Earth gravity or fractional gravity of Moon and Mars, have already been flown on multiple occasions. So top here we see an example of a centrifuge that the European Space Agency has and flown on a number of missions. Actually, this was a mission I was involved in, not using this centrifuge, but we had a payload on the same mission back in 2007. And also spinning disks, not to create gravity, but to create centrifugal forces to move fluids around. I think, as Sheela said, is already well established. So here's a couple of examples in medical diagnostic or medical veterinary diagnostics of having spinning disks to distribute fluid. And therefore, that's where we came with this concept. The core function of the ARTIS payload is in space fertilization and early embryo development to occur in a spinning microfluidic disk, so that we can create acceleration equivalent to Earth gravity. And for the kind of disk we're talking about, just to give you a bit more detail, if we have an 80mm diameter disk, so that at the center of, or from the center of rotation, we're about 35mm out, we need to spin that disk at about just under 3 revolutions per second, so not particularly fast, to generate 1G at that distance from the center. And of course, that means that we can not only use that for Earth gravity, but we can of course turn it off or modify it if we want to research other things, other gravity levels. So just to start wrapping up, this is coming back to the earlier slide. So one of the things we're trying to do in terms of the mindset is not to try and separate out IVF from space systems, to really treat it all as one whole system and really integrate at various levels our thought processes, so that there's a really intimate integration of kind of both communities, the issues of both communities in a single kind of viewpoint of doing these missions. So we see here now, so the key thing here is this IVF on the ground, and the launch segment on the ground is to really blur the boundaries of those between in terms of operations and locations and timings, and really start integrating them together so we really understand the challenges and come up with good solutions that address both communities' kind of concerns. And this last slide, just to give you a flavour of some of the things that means we're doing in more detail. I'm not going to go into the details themselves, but just to give you a flavour. So we are doing detailed system designs, kind of detailed systems workflow. As I said, integrating the details of the IVF systems with the space systems. One of the things we're doing, which of course is part of today, is to upskill or educate this really kind of varied set of actors and stakeholders, so we have a good shared understanding of each other's issues and problems. Then, of course, we've got engineering solutions. We've got to think about how do we get the biology into the bits of hardware at different stages, obviously typically very late in the kind of ground segment just before launch. So do we put them into the disks late? Do we put them into the payload late? Do we put them into the kind of hosting spacecraft late? How do we do that? What's the engineering to do that? Of course, we're exploring adaptations of cryogenics to try and get them into these kind of IVF space systems. and of course exploring alternative preservations and storage approaches. Again, Sheela touched upon some of this, and of course exploring modified IVF workflows. Again, Sheela touched upon that. So hopefully, in summary, that gives you a little bit more of a perspective from a space engineering viewpoint compared to perhaps kind of the kind of IVF viewpoint, which most of you, I think, in the audience are familiar with. But I'll stop there and happy to kind of discuss this or answer any questions as we go forwards.
Thanks, Dr. David Cullen. It was really interesting lecture. I learned a lot. For me, and I think for the majority of the audience, this topic is very new. I also congratulate Dr. Egbert for participating in a documentary that I watched while I was preparing myself to moderate this session. And I really recommend everybody to watch it on YouTube. It's Children of the Sky, Raising Kids in Space. Very, very interesting. So I'm waiting for the questions. No questions yet. And in the meantime, Thomas is going to share the video of the device.
I don't believe that we have audio here, but
I could
okay.
just comment on it for
Yes.
illustration. Here you see the satellite. Oh, you can just
Here we go.
the can just continue. It's paused now. Gradually, you can see how the segments of the rocket separate and how this unmanned small satellite, this is like a 1 meter diameter satellite, and inside you will be getting a view. You see an artist impression, a simplified version, of course. There are some IP sensitive subsystems that we cannot disclose, but you can see how the disk and the sperm cells meet the oocytes in the reaction chambers on the disk, and how the fluids are, how the redundant sperm cells are washed to a waste area. There's no sensors visible here. There's an artist impression of cryogenic freezing for safe transport back to Earth, and the rotation is stopped. And the satellite is doing a re-entry maneuver back to Earth for safe travel and for further examination of the embryos. And this is the return capsule, showing a lot of heat because of the resistance of the atmosphere with tremendous speed. And there's a parachute unfolding, and then it will be landed and picked up for transport back to the IVF labs for further examination. We had some sound behind it, but that's a technical issue today, I guess. That's the end of the video.
Awesome. Great. Thank you very much. That's fantastic. So with this device, the goal is to come back to Earth to study what happened in orbit. Very interesting. So I have some questions. Or actually, it's a comment. Brilliant presentation. Thank you all. I don't know if Nabil has a
Yeah,
question.
I have a question, more of a curiosity. So when you look at a space program like SpaceX, there's quite a bit of technology that is designed to be developed and used in space, but repurposed on Earth, right? Do and Sheila, you had mentioned the lab on chip, which is a great technology, like concept, right? A very miniature concept of IVF. Is there a chance to repurpose this on Earth in places where, there are, financial limitations and space and all of that, and the technology in general? Could that be repurposed to have a better in vitro fertilization program?
Yes, absolutely. That's actually one of our more tangible goals in terms of developing these technologies. And as we put in efforts, we wanted to make sure that our resources are, are used wisely, keeping in mind that we need to see, given that we need to raise money continue to raise money, right? As the research continues and provides more insights, we will need to have some sources of immediate applications on the ground. And to benefit that, as we understand that there is significant interest in automation and IVF laboratories, first and foremost, we want to develop a technology that will allow for easing these operations, lowering the burden of the staff, allowing for access to care in areas that are underprivileged or deprived, and more so at an economical cost. So right now, the costs are very high due to regulatory needs, and then also training. Training, staffing are significant overhead components. And by automating these tools, we're able to repurpose, the staffing and also increase volume and increase access to care, because if more people can afford it, it becomes more economical. We're obviously going to see that influx. And so that lab on a chip concept has been, explored, I would say, for a significant portion, like decades even, without necessarily reaching a fruition. Whereas this, exploration into the space environment almost amplifies, the speed at which we can make that more of a reality. So the concept, what I didn't mention kind of towards the end of my presentation is the key here is these individual chambers that the eggs will start off in, eventually develop these embryos. The samples, like the media samples, will be automated. The embryos or blastocysts will then be frozen in place, and the robotics arm or the electronic tagging system will then tag these embryos individually, so that way they are through the concept or the idea is that we'll get to a point where they're moved by a robotic arm into their final cryogenic state and storage location. So basically giving you an end-to-end automation, not necessarily just for the culture state where the lab chip has to be removed and there's a manual component where an embryologist will have to come in and manually move the final stage or the straw or the device. So in essence, the cryo device will look completely different. It'll be a complete system on this chip.
And to build upon that, that is still quite a narrow kind of perspective, in that what space does is it also makes you think about the supply chains, the building you're doing it in, because remember that we are really restricted in terms of supply chains, literally power, volume, and such. So we also have to think about, in space, what's the building that you would normally do IVF on Earth? That's got to be in space, the controlled environment. And it's got to be something which is logistically compatible with the really kind of limited kind of supply chain issues. And so it really forces you to think about all of these things in a really integrated way. Whereas without that space context to really force you to do that, you tend to, on an Earth base, you tend to forget about it, and actually to emphasize what kind of Sheela just said, you do what she did, which is not talk about the building, not talk about the trucks, not talking about the supply chain of the reagents, because you just kind of assume it's there. You don't think about it. But putting a space viewpoint on, that suddenly all gets integrated into the issue as well. And therefore, in some countries where those supply chains are not easy, the infrastructure we take for granted in some countries is not there, then this space kind of viewpoint potentially forces us to do something in space to solve these problems, which therefore then have those kind of benefits on Earth, which we perhaps wouldn't bother looking at if we didn't have the space viewpoint to force us to think about an even wider view than Sheela just communicated.
That's right.
So I have, is that okay? Someone else want to add?
Sure.
this answer? No? So I have received some questions from the audience. Hello, and thank you for this very interesting topic on artists. I'm wondering, do we currently have any time-lapse technology imaging systems to monitor embryos in the space?
Yes, so Dr. Egbert, did you want to answer that? Because I think you hit upon that in your presentation.
Yeah, absolutely. So there is a system that we are basically a subsystem that we're basically copying. There's the VitroLife embryoscope that is using, of course, the time lapse on Earth. And with our micro cameras, we're basically trying to copy that for post-mission analysis and hopefully also real-time analysis if the downlink is good enough. So we're working on this. So we intend to include this in our mini lab.
Thank you very much. So the same person also asked about the cryopreservation, if it was studied. I know Dr. Sheela already talked about this. Maybe he missed.
So what we have done is, because this is such an interesting concept, right? As we were designing this disc, and several individuals from our team with various backgrounds, right? I mean, from an engineering perspective versus from like a biological and a scientific perspective, we're all, our goals are different, even though we're looking at, okay, the end goal is having this embryo cryopreserved on this disc. Well, then from a biological standpoint, it doesn't make sense that this disc wouldn't have the ability for us to retrieve the embryos individually. So then that was another key concept that we added. So the more that we are brainstorming, the more we're learning. And with that, to Dr. David Cullen's point, is there challenges, right? These are challenges we face in terms of logistics, the space environment, robotics, et cetera. And how do we build something that we are able to utilize more immediately, but also keep, the use of our resources at the most efficient for not only the immediate purpose, but also for the larger goals, right, that we have. So we are exploring that. And there were students of Dr. Cullen that had worked on this project. So it was understanding in what conditions and in what design will the cryogenics that we thought that we could succeed with are actually successful in a spaceflight environment. So we were able to find out through their work, namely from an engineering perspective, that there are challenges in just using liquid nitrogen, which is so common to us in practice. This is just our common go-to cryogenic solution, environment, that poses so many challenges in the space environment that we may or may not be able to use that. And we may use some other cryogenic solutions, such as oxygen, or, and I'm sure Dr. Cullen can probably expand on that. But let me stop there and then have him answer the rest of it, because he is the expert on the physics here.
I wouldn't say I'm an expert, but I've obviously kind of done some studies on it. So I think the first thing to say from a space systems point of view is that cryogenic fluids in space is relatively commonplace. Remember, we're sending kind of liquid oxygen and liquid hydrogen fueled rockets. So we're flying hundreds of tons of liquid cryogen in space. So cryogenics is not fundamentally an issue. So there's two use cases at the moment for cryogenics. One is simply cryogenic liquid fuels. But of course, there the issue is, or not the issue, but one of the things that you fly in such a large amount that it's relatively easy to insulate that, because you've got a very large volume and a very small surface area that you're trying to stop heat kind of escaping from or getting into. The other use case for cryogenics in space is historically has been to cool optical or detectors in telescopes and things like that, which of course is a bit more like we want to do, very small kind of masses, you want to call just the detector of a telescope. So there are solutions there, but when we looked at those for the use cases for IVF, again, they don't really match up when you look at the detail engineering. You can't simply transfer one across to the other because of the volumes you're dealing with, the time periods you want, or in some cases just the financial costs, because again, this has got to be cost effective. And so therefore, what we realized in the study kind of was that we can't simply adapt existing technologies easily for the use case of IVF. And so therefore, that's why we're now looking at kind of other alternatives, either to completely avoid cryogenics or to use cryogenics in a different way, or to find other ways, non-cryogenic fluid ways, to get both the temperatures we want, as well as, of course, the rapid cooling. Because again, there's two things. One is keeping the temperature very low, and then the other one, of course, as you know, is to kind of do the very fast freezing so that you form vitreous kind of ice and such. And again, that becomes a different part of the challenge. And in fact, that was the key thing, that in all the use cases, the small telescopes and cooling them there, their solutions didn't need to cool quickly. They could just cool the instrument over hours or days because they didn't need rapid cooling. Once they got it cold, they could keep it there. Great. We could do that with the IVF. We could keep it cool when we got it cool. But what we couldn't find is a way of doing the very rapid cooling, where we go from, say, 37 down to minus 196 in a matter of seconds. So that's actually became the showstopper in terms of just using existing cryogenic kind of approaches that's been used already in space for other things. But I'll stop there, if that helps in terms of explaining some of the details.
I think it helps us appreciate the severity of the challenges we face, and also helps us understand that the future looks very different than what our current practices are. So we will have to learn to adapt to the new methodologies as we learn that the science is, giving us those insights for improvement.
So therefore, as you say, since we know we can keep things cool once but we can't do the rapid cooling. So that's where is there a way of evolving some of the kind of solutes we add in those in those media when we freeze, that allows us to have a much slower freezing rate, but still not form ice crystals. So again, it may be tweaking the formulation ends up being the pragmatic solution. We still use cryogens to do the long-term kind of preservation, but we just have to avoid having a workflow that requires this very rapid cooling. And that may be by just playing with the kind of some of these kind of cryoprotectors, the kind of trihalos, all these other kind of compounds may well kind of be the solution. The heat shock proteins and such may be the solution.
That's awesome. Thank you very much for your response. So now I have a question that's more ethical, political, so I think I will address to Dr. Egbert. So this person is wondering if someone already thought about how to classify the citizenship of the spaceborn baby.
We've actually had a space lawyer looked into it, and she explained this is unexplored territory. So you could wonder what's going to be in your passport for a place of birth. Is that in space? And if you're flying over a country and the birth takes 20 minutes, your place of birth is a full continent or two continents. So, but in general, it has been looked into. It's just a funny fact, and there's no precedent yet. But it's likely that there will be a similar approach, like what happens if you enter a plane? You're still in the country where you lift off from, and if you're born in a plane, usually the regulations are that you are born in the country where you lifted off from, and it's maybe Dave Cullen wants to add here.
That's a better example. So therefore, obviously, space law is something which a lot of it isn't yet well established, and so what happens is that you very rarely just start with a blank sheet of paper and generate new laws. You look to where there's existing laws which you can then translate into space, and perhaps even a better example than the airplane is a ship in international waters, because obviously there's more likely to be a birth there than on a plane. So a ship in international waters, there's already well-established kind of legal situations to therefore what that means. It means that certainly one aspect is that you're then tied to the kind of country registration of the ship. And so therefore in space, kind of one of the kind of approaches is to say, right, who authorized the launch, who is legally responsible for the spacecraft for the launch? That's the country that's relevant in terms of, in this case, kind of if you did have a kind of birth in space, how would you treat that? You would simply say, look, it's the equivalent to somebody being born on a ship in international waters, and therefore it's linked to the country of registration.
Great, great, thank you. I have another comment/question. So, incredible presentation, very informative. As scientists in such an up and coming field, for current students, do you have any classes or field work that you found the most applicable with your work?
This seems like an educational focused question, Dave, or not?
Okay, me. So I'm going to answer the question indirectly. So I've obviously do stuff in kind of space and such, and therefore go out to schools and other places to kind of do public outreach and such. And obviously, children come up and say, "Oh wow, kind of, I want to do what you're doing. How did you kind of, what did you do to get there?" And I have to say, well, it's purely by accident. I just did stuff. I was interested in things, and I was just then just able to react to opportunities as they emerge. So my recommendation is, certainly for people with my mindset, it's just to carry on doing stuff, showing interest, looking at things in detail, being inquisitive, and then seeing opportunities when they emerge. Obviously, other people have to have a much more structured approach to their career. And then I suppose in that case, yes, I'm not the best person to answer that because my mind doesn't work that way. So obviously, if you wanted to have a very specific career in this area, I would say it's a bit of a risk because it is such a niche area that if you failed, then yeah, there's not necessarily a lot of other opportunities. So I would say just look at one of the mainstream areas that's relevant, be it IVF or engineering, and just be ready for opportunities that emerge that allows you to then start bringing things together. I'm not sure that answers the
Just
question.
to add on that, in general, SpaceBorn, we love all the connections with students and universities. So we have at least 2 people graduating on a project with SpaceBorn, 3 at the moment actually. But yeah, great question.
So as you say, so at Cranfield University in the UK, we're a specialised engineering university with postgraduate only, so we have no undergraduates, but each year typically of our MSc course in astronautics and space engineering, which is primarily for space engineers, we typically have 1 or sometimes 2 students which do projects associated with SpaceBorn, looking from a space engineering perspective at various aspects. So we've done kind of mission designs in the past. We've looked at some of the cryogenics with kind of Cranfield master's students doing master's projects. So again, that's another way. It's if you're at university level having to do projects as part of your kind of education, then if it's something where the project could be relevant to SpaceBorn, then I'm sure there's the ability to kind of have some kind of either formal or informal collaboration with SpaceBorn, where there's a win-win situation where the kind of student gets to do something relevant to space, biology, IVF in space, and SpaceBorn gets hopefully a pair of hands to do something which is valuable for them as well.
That's interesting. I think you need to create an educational program, and it involves multi-specialties, right? So another person.
Yeah, I have a quick question for the team, Sheela in particular, and also for the rest of the team. So the environment in space obviously is going to be very different from high gravity environments. And so cell division may be different. Chromosome segregation may look very different, right, from what we see. And the way embryos grow over time may also have different time lapse time and right timing. And then you can add to that all this metabolic ability to metabolize certain nutrient versus others. Are we going to adjust to a new way of interpretation and analysis
I
if
believe,
that happens?
yes, I believe we are. The expectation is that we are going to learn from this, the series of experiments, the exact effects of the various levels of gravitational forces and the biomechanisms. And once we understand what the impact of those are and at what areas we can intervene to help the developmental stages of the embryos, you're right, the checkpoints might look different. Inherently on the ground, we are designed and programmed, and over evolution, we are surviving at this, at a certain rate of cell division, which we determine to be normal. But under these altered conditions, the embryo is incredibly, displays such a high level of plasticity. We expect that the embryo will develop despite these stressors, and then once we identify how we can help the embryo overcome these stressors, we'll be able to identify these new checkpoints or these new biomarkers that will help us adjust our flow and our IVF processes. So yes, to support the points that we've just made, IVF might look very different in the future as we discover what our research is. Offers insights into the new way of IVF. The new way of vitrification might not be how we freeze embryos or cryopreserve embryos. We might have a completely different approach. And IVF might look very different in the future in terms of, completely hands-off and the testing I expect to be very different, whether that would be screening or more diagnostic, because we are hoping that we can incorporate multiple diagnostic and screening approaches and give a more comprehensive approach. The time-lapse imaging that we had discussed earlier, I think that's pivotal as well, because as we make these adjustments and we find that the time-lapse checkpoints are different, as you know, the recent publication that was available through, the Alpha Scientists group and ASHRAE, it's the Istanbul Consensus. It was heavily focused on discoveries made through time-lapse systems in terms of what is the appropriate fertilization time, the appropriate cleavage times for like T2, T4, etc. And it was very different from what we considered to be normal. So times were adjusted by an hour on each side, which is significant, and it really alters how our workday is programmed. So as we open up to adopting more time-lapse technologies, it helps us expand our workday and expand our ability to incorporate changes into the work environment, into the embryo culture and biology. So it'll be very fascinating to see how we can utilize these new technologies and hopefully be able to expand not only our science and our understanding, but also our complete outreach and how we perform IVF in general.
Thank you very much. I have another question here. The person is also congratulating everyone. Excellent presentations. And they are curious about if in these studies that you mentioned, I think especially in this one in the Cape Canaveral, if you used human embryos or gametes, or it was mouse gametes.
So if you're talking about the Cape Canaveral launch, so this is the launch that's already happened in April of this year. The key thing there was no biology launched. It was just launching hardware, because so remember that going forwards, we are doing, if you want, space stuff in a very different way than we have in the past. In the past, because access to space was so rare, you had to do everything in one mission, one launch. Whereas nowadays, because of SpaceX and a number of other things, we can now, there's so many launch opportunities relatively, that you can now actually have a series of launches to develop your payload over time, rather than just develop it on Earth and fly it once. And so therefore, we've got this whole series of kind of flights planned, which each makes a small step forward in adding more and more complexity into the system. So this first one was really quite a simple bit of hardware, where we just flew it to both understand it would work when we flew it, but also that we could handle all that ground segment beforehand. And so it was hardware only, no biology in that first one. Going forward, then I'm assuming that I'll hand over to kind of Egbert, but I assume we'll start off with model mammalian systems before we then go on to human stuff. But I'll hand over to Egbert now.
It's not a secret that there was a little bit of biology on board. Inside our mini lab, there was a little bit of extra volume that we didn't use, so we allowed a small other experiment that contained some yeast cells, which also helped validate our life support system. But it's not mammalian cells or anything. That's all.
Okay. Yeah.
And
obviously it's more subtle than that, but yes, I won't disagree.
And this person is also asking if has been already fertilized human embryos in space and born on Earth?
No.
No. Okay.
Absolutely not. That's a big step. We hope to be the first with that.
Okay, but studies have been made with human gametes, right?
Frozen sperms.
That's right. Frozen sperm cells were sent into space, and various conditions, right? So they weren't sent into the space environment live. They were sent. So they were, of course, procured on the Earth, frozen on the ground, then sent in a frozen state up to the space environment, then brought back, and testing was done just based on the frozen state exposure. So it's a very different concept than if you look at germline cell exposure. So if you send a live human up into space, and then the germline cells are potentially exposed to space radiation or longevity in terms of microgravity or variable gravitational conditions, then and other stressors, then that becomes, obviously a more challenging and complex system, because now not only are you dealing with isolated reproductive system or organs or cells, you're dealing with the whole body environment. And and in that particular case, then the outcomes are going to look very different than if you look at just particular tissue only. So in terms of in the research that I've looked at, the mouse model mice have been sent into space. There was a live C-section recorded of a mouse in the space environment, which was pretty fascinating. But otherwise, in terms of human, that's the extent of what we've done. And the majority of that comes into play because of the ethical regulations of the various, countries that we just don't know enough about the impact of the space environment onto, our ability to reproduce and the impact that it would have on generations to come, when we're looking at the generation that was exposed. So those limitations are what we're working on in terms of our science and our research, and hopefully we'll be able to inch forward, and one day we'll be able to say that we have done that, right? That's the goal.
I've got a question for Sheela. So obviously you've got to deal with the ethics. It's not really a research project, but clearly female astronauts have flown in space. They've come back, and then they have had families, they've had children. So clearly there is a set of humans who have flown in space, been exposed to space environments, microgravity, for potentially months, come back and had, as far as we know, successful pregnancies, kind of obviously initiated after flight, but with those cells that have been exposed for a period of time to space environments. Obviously you can't treat that as an experiment, but that has happened, that's fact. And we know that there isn't, as far as I know, there isn't any major knowledge about any kind of deformities or issues. So how does that all fit into this? Is that a sensible viewpoint to take, that we do have some evidence, it's just we can't really treat it as an experiment?
Yeah, there's definitely evidence, and there was, awareness being raised so now NASA has like specific physicians that are dedicated to female reproductive health. They have OBGYNs on their staff because they know that this is a concern, and we need to protect our astronauts and our young scientists from being able, from being hurt into when they're in their space environment. In terms of research so yes, live people that have gone into space have returned, and yes, they have been, reported successful pregnancies thereafter the space exposure. But we haven't really explored, the long-term effects of these children that are born. So that's an area of focus that we have that we hope to gain understanding. But when we send, for example, the tissues, for example, mouse ovaries or ovarian tissue, there are reported studies that show that there is a decline in the follicular numbers and the health of the follicles. And that is not once returned to so like in the live mouse models, and once returned to the Earth environment, they were not able to overcome the losses. Whereas in the male mice, they were able to overcome the depletion of cells and the impact of the space environment with the cycle that, obviously is available in like the male versus the female form. So these are interesting challenges that we face. And of course, with more longer term studies, we'll be able to answer that question with more accuracy. But at this point, we don't have the cross-generational effects, which is what I'm more interested in.
And so in terms of astronauts, is there any kind of emerging practice where kind of both male and female astronauts will, prior to flight, will try and harvest and store reproductive cells just
Yes.
to minimize that chance? Is that becoming established practice, or is that a known kind of approach that some astronauts take?
Looking at it from more of an IVF view, there has definitely been more awareness and more educational, attempts at making sure that the science of preservation is an option. And we have, as far as in the IVF community, worked tirelessly to improve our practices so that way when cells are frozen, when gametes are frozen, that downstream patients are able to rely on the use and the quality of these gametes once they're warmed. And nowadays, even in terms of, insurance and medical coverage, et cetera, they're opening up options to where that has become more and more normalized as a practice. So yes, the practice is available and out there. There's definitely awareness. There are campaigns, and especially, like for breast cancer or ovarian cancer, testicular cancer patients, there's a separate campaign there. So for the general population, there is awareness. For the population of scientists that are particularly exposed to the space environment in terms of astronauts and young individuals, with the help of more organized workflows, there's definitely options, and more are opting to cryopreserve their gametes ahead of the space flight.
That's great. Thank you for your answer. Well, we don't have any more questions from the audience, and it's been 90 minutes. It's almost 1 a.m. for Egbert, so I think we can end this webinar, and I thank you all for the participation and sharing your knowledge and time with Progenesis.